What's good, everybody? Welcome to a video on the mechanism of metformin. Before we get into the particulars of that, just a little bit of background on metformin. Metformin, you can see here on the right, is a biguanide molecule which was derived from a guanidine molecule in the French lilac plant that scientists discovered in the late 1800s helped to lower blood sugars in rabbits. And they found once they created metformin, it did the same thing in humans and was even more effective. So the desired effects were improvements in insulin sensitivity and blood sugar. The side effects, certainly GI disturbance, potentially nausea or vomiting, and lactic acidosis, particularly if you have kidney issues. Contraindications include serious kidney issues, heart failure, and acidosis. Finally, this last diagram on the bottom right here shows that all of the different health benefits that metformin confers start from its increase in AMP kinase. And so we'll follow each of these different pathways and explain what's going on and why it's occurring. First and foremost, metformin enters the cell through the OCT1 receptor, and it accumulates in the mitochondria and ultimately inhibits complex 1 and complex 4 of the electron transport chain. I have a few videos on how ATP is made and why ATP is a unique molecule, which could help delve into the particulars of those. But ultimately, this inhibition of these two complexes cause a drastic decrease in the amount of ATP that's produced and an increase in one of its metabolites, AMP. So instead of having 3 phosphates, the adenosine just has 1 phosphate in adenosine monophosphate. And so this increase in AMP will activate the AMPK kinase. And so you can think of, if ATP is the primary kind of energy molecule in the cell, and AMP is when you don't have enough ATP and it's degraded, the ratio can tell you whether the cell is in an exhausted or an energetic state. So if there's significantly more AMP, you're stressed, and that will induce all of the different cascades that we're going to talk about. Why some people could maybe refer to metformin as exercise in a pill, because similarly to metformin, you can also increase AMP kinase through exercise or metabolic stress or exhaustion in, just everyday life. So the mechanisms that occur when AMP kinase is increased includes inhibition of AS160, which you can see here in the diagram. So AS160 normally inhibits this RAB, and because AMPK inhibits AS160, this means that the GLUT4 translocation is free to translocate to the membrane and help to increase glucose uptake into the cell. So it's kind of a two negatives make a positive scenario. So because AMPK inhibits something that's inhibiting the GLUT4 translocation, it's actually activating the GLUT4 translocation of the membrane. And so if you can increase the amount of glucose that's uptook from the blood into the cell, then your blood sugar is going to be lower. Furthermore, AMPK also has effects on how fat in your body is used. So it decreases fatty acid synthesis, meaning creation of fat to be stored in your body, and increases beta oxidation of fatty acids, meaning the breakdown of fats into forms and be used in the electron transport chain to create ATP as energy. So overall, this process helps to encourage your body to use fat as a source of fuel as opposed to glucose, and lowers your blood sugar as well. So we'll kind of start with the diagram up here. The AMPK inhibits the ACC acetyl-CoA carboxylase enzyme, which will decrease the amount of fatty acid synthesis. You can see that up here, but also if you go down to this diagram here, this ACC is also this ACCase. So if you can't even start the reaction to fatty acid synthesis, then you can't synthesize fat to be stored in your body. Furthermore, it inhibits the suppression of CPT1 by melanoCoA, which promotes fatty acid oxidation. So this is another two negatives make a positive, in that because it's inhibiting something that's inhibiting something else, it's activating the pathway. You can see that down here. So up here you have pathway, of course, shows it inhibiting CPT1, but also in the diagram down here you can see CPT1 right here. If it's not inhibited, you can follow the pathway all the way down until, through beta oxidation, which produces acetyl-CoA, which can then be used in the citric acid cycle or the Krebs cycle to create ATP. Moving on, AMPK also inhibits transcription factors that promote gluconeogenic enzymes. And gluconeogenesis is just the production of glucose, so raising your blood sugar. So not only is it increasing the uptake of glucose from your blood, it's also increasing the amount of fat you use, and it's also decreasing the amount of glucose that you create to put into your blood. In this case, you see AMPK kinase. It'll inhibit all of these downstream transcription factors that would eventually help to produce PEP-CK and glucose-6-phosphatase, which you can see on the diagrams here. The PEP carboxykinase, which is the secondary enzyme for gluconeogenesis, and then also one of the last steps in gluconeogenesis, glucose-6-phosphatase, that make glucose-6-phosphate into glucose. Those are the two enzymes that are being downregulated by the inhibition of these transcription factors. Last, this is a little bit less studied mechanism, been getting a little bit more traction lately because of the popularity of the microbiome as a topic. It has been shown to increase certain types of good bacteria and decrease certain types of bad bacteria. I don't want to get too deep into this because ultimately a lot of the research on the microbiome is really just correlative, meaning they see certain types of bacteria in certain conditions and other bacteria in other conditions. It's not entirely clear what's good and what's bad, and we just need to replace this. For the most part, the consensus is just it's good to have a variety of bacteria in your microbiome. I hope this video has been educational, and have a good rest of your day.